All right, this is the section 3.3 extra examples, concavity and the second derivative test. Remember, concavity has to do with whether or not your graph is curving upward or downward. And if you do two derivatives, you can then determine whether or not you're concave up or concave down based on if that second derivative has a value at the test value that is either positive or negative. So when we look at a concave upward, notice f prime is increasing. When we look at concave downward, notice that we have f prime is decreasing. So to determine the open intervals of which the graph of f of x equals 5x to the fourth minus 20x is concave up or concave down, we need to take two derivatives. So f prime of x would be 20x cubed minus 20 for the first derivative, and then f double prime of x would be 60x. The point here where f double prime equals 0 would be at 0. So if we make that in our chart and we pick a test value on each side, so let's say -1 and +1, we plug those into our second derivative. So this would be 60 times -1, which is -60. This would be 60 times +1, which would be +60. This is an overall negative. This is a positive. So that means this part is concave downward, and this part is concave upward. Okay. So that's how we see that. So you can write the open intervals. You could say on -infinity to 0, I'm concave down. And on 0 to infinity, I'm concave up. Okay, let's do another one. So in this one, we want to determine the open intervals on which the graph f of x equals x squared minus 9 over 8x plus 7 is concave upward or concave downward. Do notice that there is a discontinuity here at 8x plus 7 cannot equal 0, so that would be -7/8. So that's just an undefined place for the original function. So then when we're going to look at the derivative, we need to take the first derivative. Now this is a quotient rule, so my top, I'll write it out here, is x squared minus 9. So top derivative would be 2x. My bottom is 8x plus 7, so my bottom derivative would be 8. So for the first derivative, derivative of the top times the bottom, which is 8x plus 7, minus the top times the derivative of the bottom, all over the bottom squared. So let's work out the top, because we still have to fix this before we can go on to the second derivative. So this would be 16x squared plus 14x. There's an 8 here that I have to distribute as well as that negative, so -8x squared and plus 72 all over 8x plus 7 squared. F prime of x then would be 8x squared plus 14x plus 72 on top, all over 8x plus 7 squared. So let's go ahead and take the second derivative. So then we need to look at the top this time. So I'm going to kind of separate this out. Is 8x squared plus 14x plus 72. Top prime would be 16x plus 14. The bottom is 8x plus 7 squared. The bottom prime would then be a chain rule. Pull the 2 to the front, you have 8x plus 7 to the first now, times the 8, or just 16 times 8x plus 7. Now I'm going to leave that unfactored for just now so that we can write this out. So the f double prime is the derivative of the top times the bottom. Might want to write this in parentheses too, minus the top times the derivative of the bottom, all over the bottom squared. Now the bottom was already squared, so it's going to end up being to the 4th power. Now I'm going to increase some space to write the rest of this out. So the big thing we need to worry about is how this is going to clean up. I do believe that this 8x squared plus 14x plus 72 is factorable, and that might help us, but it might not. So maybe we'll just leave that alone for now. But we do see that this has a GCF we could pull out. You can pull out a 2 right here, so that would make that 8x plus 7. Okay, so that makes that a little easier. So this, I'm going to rewrite this as 2 times, not 8x plus 7 squared, but now 8x plus 7 cubed, minus, I have a 16 right here. I have an 8x plus 7. And I don't think this is going to factor into anything that's going to help us, because for this to factor into another 8x plus 7, we would need it to have something in the end that's divisible by 7, and 72 is not divisible by 7. So I think we're just going to have to work with what we have. So we need to just factor out what these two tops have in common. They both are divisible by 2. And they both have at least one 8x plus 7. So that leaves us with 8x plus 7 squared minus 16 divided by 2 would be 8. And then we would have the 8x squared plus 14x plus 72 all over the 8x plus 7 to the 4th. We need to clean up what's inside here, but we also can cancel out one of these with one of those. So that makes life a little bit easier. So see, this one's really, really hard, something we normally wouldn't put on a testing situation. So I have a 2 out front. I need to FOIL this. So this would be 64x squared plus 56 plus 56. So that's going to be plus... that'd be 112, yes, x. And then 7 times 7 is 49. Then we need to distribute this negative 8, so that's negative 64x squared. So the x squareds are going to cancel out. 14 times negative 8, off the top of my head, I don't know. So 14 times 8, so that's negative 112. So the negative 112 x's are going to go. And then we have 8 times 72, and it's going to be negative, and that's negative 576. So quite a few things are going to cancel out on the inside in there. And then this is 8x plus 7 to the 3rd. So my 64x squareds are gone. My 112 and negative 112x is gone. We just have 49 minus 576. And that's negative 572 times the 2 that's out front. So negative 1054 all over that. Okay, so let's look at what we have. Okay, so remember these possible places where we're looking at, does it go concave up or concave down, is either where the top equals 0 of the second derivative or the bottom. So the top can never equal 0. So I'm going to kind of go over here and do my chart. So top does not equal 0. The bottom would equal 0 at the undefined, remember, discontinuity. So at x equals negative 7/8, we have something undefined. Okay, we still put that in our chart because we could be concave up and concave down on either side of that. So negative 7/8 is our splitting point. So something smaller would be like negative 2, something bigger could be 0. Plug those into your second derivative, We plug in -2, that would be -16 on the bottom, plus 7, that's -9. You cube it, it will still be negative, so that would actually make a negative divided by a negative. So this is going to end up positive. So this region is going to be concave up. And then if we put in 0, that just makes 7 cubed on the bottom, so that's positive, but it's a negative divided by a positive, so it's a negative. So that makes that concave down. So we are concave up from -infinity to -7/8, and we are concave down from -7/8 to positive infinity. I wanted to pull this one up on a graph, so I already did this, so you can see what we're really getting here. Notice there's not like anything really existing at -7/8 because that is an undefined value of the original function. So you have this vertical asymptote right there. But on this side, we are definitely concaving up, and on this side, we are concaving down. So it does give us the correct intervals. Okay. So remember, the next thing we learned about was points of inflection. These are the points that when the second derivative equals 0 are undefined, it is possible that you have a point of inflection. Those are also usually maxes and mins. Relative maxes and mins are found by this test as well. So how we know that we actually have what's called a point of inflection is that we see the sign change when we look at this. So if we don't have a sign change when we do this test for concavity, then so if you have 2 pluses back to back or 2 minuses back to back on the second derivative when you plug in, then that means you don't have an inflection point. So all the ones we've seen so far have been inflection points. The second derivative test, just to summarize what we said in class, allows us to figure out things about the relative maxes and mins as well. So the second derivative test says if you take a derivative and at your critical value, you plug it in and it equals 0. So f prime, so this says you have critical values from the first derivative. So you have to know what those critical values are, okay? If you know what those critical values are from the first derivative and the second derivative actually exists, then when you plug those critical values into the second derivative, if they come out greater than 0, then it's a relative minimum because that means it's like this, because it's concave up. If the second derivative comes out negative for that critical value, that means you're concave down, so you have a relative maximum. If it equals 0, then the test fails, and you should go back to looking at whether or not you're increasing or decreasing using the first derivative test. Now, we've done most of these in the notes in class, so I'm going to skip to something we did skip over. Remember, point of diminishing return is also just an inflection point. We did not do these sketching ones at the end of the notes, so I want to make sure we go through those. So sketch a graph that has the given characteristics. So this says f of 0 equals 0 and f of 2 equals 0. So think about that as saying, split it up. F of 0 equals 0, f of 2 equals 0. That's actually 2 ordered pairs. That means 0, 0, and 2, 0 are on our graph. So before I do anything else, I can at least plot those points. I'm going to plot them in red. And then 2, 0. So let's get some other markers around. Okay. Now, the next thing says your first derivative is greater than 0 if x is less than 1. So remember, here is x is less than 1, somewhere right around here. We don't know how high up it's going to go. So we're just looking at this as kind of a rough sketch. But they say when x is less than 1, because our f prime is greater than 0, remember that means we have an upward slope or positive slope. Or another way of thinking of that is increasing from left to right. Now, at f prime of 1, we equal 0. When you have an f prime of x equal to 0, you have a horizontal tangent line, which remember means your slope is 0. So that's going to be a relative max or min, okay? And then f prime of x is less than 0, so that means negative if x is greater than 1. So if x is greater than 1, we're going to be going downward, negative slope, and decreasing is another way of thinking of that. Okay, and this says f double prime of x is always less than 0, so that means we're concave down. Now we don't have to know how high this point actually goes, and in fact I probably should not have even drawn any y points, so let's just take those off. We don't care about how high or low the actual y-axis points are getting, we just care that we've got the description correct. So it says at 1 for x, so that's right here, we should be having a horizontal tangent line, which means we should have a max or a min. Now the reason I'm going to draw this above is because on the left side I'm supposed to be going uphill to that point. On the right side I'm supposed to be going downhill from that point, because that's what these two things tell me. And then the whole graph is supposed to be concave downwards. That does match with what I'm doing here. So this is really just a description for an upside down parabola using nothing but calculus information and some intercepts. So let's look at this next one. It says f of 3 equals 0. So again, that's like an ordered pair, 3, 0. F prime of x is greater than 0 for all x's. So that means we're always increasing our graph. F double prime of x is less than 0 if x is less than 3. So that means from negative infinity to 3, we're concave down. And from greater than 3, we're going to be having a second derivative that's positive or greater than 0. So from 3 to infinity, we're going to be concave up. Okay, so let's see if we can sketch what this would look like. And again, I'm not going to put any y points since we're not really too worried about how high some of these points are getting. So 3, 0 is our x-intercept. We're always increasing, so that means as I draw from left to right, my graph should be going up a hill. And then from negative infinity to 3, I'm supposed to be concaving down. But from 3 to positive infinity, this direction, I'm supposed to be concaving up. So there's a rough sketch of that one. Okay, let's look at the last two problems here in section 3.3. Let me get this all together on the same picture. It says use the given graphs to determine, this is y equals f of x, and we're going to be trying to sketch the graph of the derivative. Okay, so there's some things you have to know about sketching the graph of the derivative. And I'm going to try to write them. So this picture over here is supposed to be f prime of x, and this is f of x. So here's some things to note. Relative maxes or mins from f of x are places where f prime of x was equal to 0. In other words, an x-intercept over here. Okay, so notice at -1 we had a min here, and at +1 for x we had a max. Because those are mins and max x values right here, this one and this one, those are then x-intercepts on our f prime, because that's when f prime of x would equal 0. So -1 and +1. Okay. Other things that you can note about the original function. When is it decreasing? Concave up, concave down. When is it increasing? On this side, I am decreasing from negative infinity to -1. From -1 to 1, I'm going to be increasing. And from 1 to infinity over here, I'm decreasing again. Now there is one point that's kind of hard to see. Right here, this is the point 0, looks like 1/2. Yes, 1/2. This is an inflection point. Okay. So what we know about decreasing, increasing, and decreasing is that on here, When you have a decreasing part, your f prime of x is less than 0. If you have an increasing portion, your f prime of x is greater than 0. So that tells us when are we above or below the x-axis. So this would be below the x-axis. This would be above the x-axis. So looking here, we can say, okay, from -1, this direction, we should be below because it's decreasing its slope. Remember, this is actually a graph of what the slopes are doing. And then also from 1 down to positive infinity on the x-axis, we're also decreasing. So this is also going to be going down. The middle is an increasing part of the original function, so we should be up, but there should also be a place where we have something called, remember, an inflection point. So when we talk about that, this 1/2, that's actually going to be the place where we change from concave up to concave down. So we have to be careful with how we draw that. So what we have to remember when we graph this inflection point is that when we say we're graphing the derivative, we're graphing actually the slopes of the original function, of those tangent lines. So if you're graphing this point right here, just any random point, you find what x value that's tied to, and that would tell you the slope of the tangent line at that specific point on the original function. So we can kind of figure out the slope here just by kind of counting it. This looks like it's right 1, up 1. So this looks like it has a slope of 1. So that's why my inflection point is going to have a max height of +1. Because that is the slope of the tangent line at 0, 1/2 on the f of x. So now we know that, we can kind of fill this in. This is supposed to, remember, be positive slopes, positive slopes. So connecting all of those pieces. So this is the graph of the derivative of this function right here. So let's do another one real quick, and that will be, I believe, the end of this section's notes. Yes. So when we look at the one down here below, let's see if we can pick out that information as well. Sorry, my graph's not wanting to slide down. There we go. Okay, so again, we're looking for maxes and mins to figure out where we're going to have x-intercepts for the derivative. So it looks like at, and this one's a little bit harder to see, this is -1, and it's counting into 1, 2, 3, 4, 5 blocks. So this point right here, this would be -1.246, so -1.6. This one right here, it's a little hard to see. That looks like it's exactly halfway, so maybe -0.5. And then down here, this one looks like it is 1.2, 0.4, so maybe 1.3. So a little bit harder to see on this one because we're estimating where we think those maxes and mins are. So remember, those are going to be x-intercepts on our new graph. So -1.6, 2, 4, 6. -0.5, so halfway between 0 and -1, and 1.3, so just a little bit over that way, in between 1.2 and 1.4. They're counting by, looks like 0.2s. Okay, and then we can talk about increasing, decreasing stuff. So this is decreasing from here to here, increasing, decreasing, and then increasing again. And we should have some points of inflection. It looks like this one right here at -1, 0, we had a point of inflection, and at 0.246, so 0.6, -1, we also had a point of inflection. Just eyeballing what I can see here. That's from where we changed from being concave down to then being concave up. There's a texture change in which way it's caving in or out. So when we try to graph those, remember, we'll have to have them as their slopes. So this one looks like it also has a slope of 1/1 for the tangent. So that means they're going to have a max height of 1 at -1. And then this one, it looks like the slope is, we're just going to have to guesstimate, Looks like it's down to right 1, so down to right 1, so -2. So at 0.6, we're going to go all the way down to -2. Okay, and then let's see if this makes sense. From negative infinity to -1.6, we were supposed to be having a derivative that was decreasing, so that means we're below. From -1.6 to the -0.5, we're supposed to have an increasing slope for our tangent. So that means we have a derivative that is above the x-axis. From -0.5 all the way down to 1.3, we are supposed to have, which is over here, we're supposed to have a decreasing slope. So we're supposed to have something that is below the x-axis. And then from 1.3 to infinity, we are supposed to have an increasing, which means it's going to be going up. So there we go. That is the graph of the derivative to the best of our ability by estimating the maxes and mins, the increasing, decreasing information, and looking at the slopes at those inflection points. All right, hopefully this was helpful for everybody.